vector, which goes 1 forward, nothing up and down. The j vector is just 0, 1 vector. It goes up but doesn't go left or right. Alright? So when you think about it, this is essentially 1, 0 plus 0, 1, which you would get your 1, 1 back. Alright? Now I could have another vector like 2 and 3, which when you think about it, this is going to be 1, 2, 3, 1, 2, 3. That's here. So you could describe this as going 2 i's plus you go up 3, so it's 3 j's. So you can describe your vector. Now, anywhere in this plane, you can go with combining I and j. Like anywhere you are in this plane, you can somehow find a combination of I and j to get there, right? Okay. So these I and j are called the basis for your plane, which means they're the building block of your plane. You can build this entire plane out of these 2 vectors. So this I and j will be the building block of this entire plane. Okay? And essentially what you say is that I and j span R2. Or you say I and j, I don't get into the technicality of it right now, what does it mean? I and j are the basis for R2. So you can essentially span anywhere in this plane with those 2 vectors, because you can just combine I and j and get there, okay? Now, what happened is that someone comes and gives you 2 vectors and says, someone comes and says, I have this 2 vector, v1 and v2, and I can actually span my R2 using these 2 vectors. How? I can combine them like this. I can say, this is my point, like 1, 1. I can span anywhere in the space, but everything is essentially fucked up. Everything is crooked. You know, everything is like, you're defining your entire space using v1 and v2. So yeah, you can get here. What is that coordinate for that? That's like 2 v1 and 2. So this vector here is 2v1 plus 2v2. That's this vector from here to there. All right. So you could define a whole new set of rules and things on the space using v1 and v2. And the reason they do that is because you actually, sometimes you're dealing with things and spaces that you don't have the basis. As soon as you find them, you want to use them. All right. So, but that's not comfortable. That's not like easy to deal with. Everything is kind of like on an angle. You have part of this and that and part of this and that. So there is a process that you can take this 2 vectors, you can take this v1 and v2, you can take this v1 and v2, and you can make these v1 and v2 into nice little bases. How? You can make this v1 into a shorter v1. Okay, so let's call this some w1, which is in the same direction as the v1. But then instead of having it on the direction of v2, what we could do is we can find an orthonormal or orthogonal with the length 1 vector and call that a w2. Now you can see this w1 and w2 are very similar to your I and j here, right? But the goal is to get this W1 and W2 from this V1 and V2. All right. So this process of taking your input is V1 and V2. Your output is W1 and W2, and these are two vectors that span a space, the two-dimensional space at least here. And then here, W1 and W2 are two orthonormal vectors that span the same space.
Just a reminder, orthogonal means at 90 degrees to each other.
Orthogonal means 90 degree. Orthonormal means 90 degree with the length of 1. So that's all it is. Now this process is called the Graham-Schmit, is that how you do it?
Yes.
Process.
No H on the end.
This is called a Graham-Schmit process, which your input would be any two vector that will do the spanning. The output would be two vectors that are orthonormal to each other. All right, and this is done very easily. It's done with this whole projection stuff. So, so the way to do it is the following. I'm just going to do it with the two vectors right now, and then if with the three vectors we can just look it up later. So let's say you have V1 and V2. Let's make it a little shorter. And you want from this, you want W1 and you want W2. The way it works is that W1 is very easy to find. All you have to do is take, so W1 is you take V1, which is a vector, and you divide it by its length. If you divide something by its length, then the total length would be 1. So it would be V1 divided by its length. That's how you find the W1. Now, so this part is easy. The second one gets a little bit trickier, and let's look at it. In order for me to find this, I need to do this. I need to look at this V2 as the following. I need to look at this V2 as a combination of this vector and that vector. So this portion is called the projection of V2 onto V1.
If you remember last session we wrote a short function to do that, to take the projection of one vector on another.
And all it is that imagine you have like some sort of light up here. If you shine down, where is the shade? The shade is down there. And in order to do that, there's something called a dot product. At least we talked in linear algebra class. We talk about inner product as a general, but at least for Calc 2 students, you can think of it as the dot product, where if you have two vectors and you multiply them, so the multiplication of the dot product multiplication of V1, V2 is the length of V1 times the length of V2 times the cosine of between them. And this is the angle between them is called a theta. All right? Now, all projection is that if you look at this triangle, and you want to find that size, you can use a law of cosine, right? What is the cosine of theta here? The cosine of theta here is this over that. So it's the size of the projection over the size of V2, right? So I can figure out the size of projection. So I can say the size of the projection of V2 over V1 is just V2 times the cosine of theta. Alright? So that just comes by cross producting these two. So I can find the size of this. I can find this direction. This direction is easy. I already found it. That's just V1 over V2. Over V1 over its size. So this projection guy can be figured out as, so this projection of V2 over V1 can be figured out as the size of that times this direction W1, which is V1 over the length of V1. That gives you the vector, because I have the size, I have the direction, I can find it like that. But then let's dig into this a little bit more. Look at this definition I gave you for the dot product. You can figure out the cosine, right? Cosine is this dot product divided by the two lengths, which is V1 times V2. So I can plug that in to here, so this becomes V2. So this is the size of the projection, is V2 times V1 dot V2 over the length of V1, the length of V2. And you see it cancels out. This guy cancels out. So you have V1 dot V2 over V1. That's the size of the projection. So let's plug that in over there. So this becomes this projection, which is V1 dot V2 over the size of V1 times this vector V1 over the size of V1. And if you simplify this to, you get the following. You get V1 dot V2, then V1, the size of V1 squared times V1. So that's called the projection of V2 over V1. It's a formula that on its own doesn't make much sense, but where it's coming from, it's what is the dot product of V1 times V2 over the length of V1 in the direction of V1, because we're essentially, this projection is in that direction. That's why we have that V1 guy over here, and this kind of adjusts the size for us. Now, why did we find this projection? Because if this is the unknown vector x, projection of V2 to V1 plus x gives us this V2. So if I'm looking for V2, if I'm looking for x, x is just V2 minus the projection of V2 over V1. So that's that second vector that I was looking for, because I want the Graham-Schmit process want to make these into orthogonal, right? So that's that orthogonal component which comes from V2 minus the projection of V2 over V1. And that I can use that over there, so this is what I would do. So I say this x is V2 minus what I just found here, what this V1 dot V2 over V1 the length squared times V1. Now this x essentially is this. I found this is V1, this is V2. I have my W1, right? And I have this x, and all I have to do is W2 is just my x over the length of x. And that's how I find my second vector that goes up. So I can find this W1 is here, and this W2 is there. So W1, if you remember, is just V1 over the length of V1. So now I have two vectors that are orthonormal to each other. They both have a length of 1, and I can define, I can span my space, I can span this plane with those two vectors. I could have done it with V1 and V2, but if you saw, it was all crooked. Now I have two beautiful unit length orthogonal vectors to each other that I can, span over the space. So this whole process is called the Graham-Schmit, and that's what you guys are going to code. Yes?
What's the real world application?
Well, one that we're probably going to be doing next week is linear regression. When you have, say, you take a bunch of experimental data and you think it should fit some y equals mx plus b, but it doesn't exactly because you've got little variations, so you can't just plug it all in. And so you can't just look at it on a graph and kind of draw a best fit line and try and figure it out. But you can use the Graham-Schmit process as one method of finding a more advanced, a more accurate regression of a series of data points. So that's just one off the top of my head usage. Like you were saying, a lot of the times a lot of higher math is converting things from one set of, what's the word I'm looking for? Basically from one format into another format that is easier to work on them in, and then back to the original format. So say you have something that's not very nice as your basis, but you need to end up in that. You can use Graham-Schmit to convert to something that is really easy to work with, do all the hard math there, then reverse it to convert back to your original basis, and that's your actual answer.